All right, sorry for the delay, everyone. We had some technical difficulties. We're going to talk today about check valves and relief valves in unsteady flow. So basically what you would see in AFT impulse, and really just talk pretty high level about why you should be concerned about these devices, why they might pose a threat to your system, even if you're not really considering them as a primary driver of transient events. So my name is Scott Lang. I'm a lead engineer here at AFT on our thermal fluid system simulation team. That really just means that I, along with my co-presenter Mark, we work on the simulation code for our solvers, building that up and making sure that you're getting good results. And I'll let Mark introduce himself either now or a little bit later when it's your section.
I can introduce myself now, yeah. My name is Mark Dudley. I'm a senior software engineer on the same team as Scott. So we work pretty closely, as he said, on kind of the back end, ensuring that your results aren't misleading you. Yeah.
All right. So this presentation is really a brief version of a couple papers that Mark and I wrote. We presented these at the ASME Pressure Vessels and Piping Conference in Seattle, Washington earlier this year. I presented my paper, and another co-author on Mark's paper presented that one, Devin Rohrabaugh. We also wrote these papers with Jan Schroeder from Mockfeld Valves, so that company makes specialized surge check valves and relief valves. And also Dylan Whitty works for Brown and Caldwell, and he has tons of experience applying these to real systems and in particular real impulse models. So we have a lot of experience that went into these papers. They are overview papers, just talking about a lot of stuff that people already know, but we've tried to collect a lot of information in a central location to get people started in understanding how these behave. The links to these papers will be on our website soon. They're not up there right now, but sometime soon you'll be able to get those in our learning center if you're interested. So the motivation for this investigation that we did was, first, as I mentioned, check valves and relief valves are both common. You'll find them in just about any system, but the design and specification of those is often rooted in steady state perspectives. So people will size them for minimizing loss, things like that. But really, these are transient devices. If they weren't transient, they wouldn't do anything. And often, by design, their operation can be extremely rapid. So you want a check valve or a relief valve generally to act quickly. And if it acts quickly at the wrong time, that can cause some pretty extreme pressure surge, both high and low. And that pressure surge, just for background for people that need the additional primer here, that's going to travel at the speed of sound through the entire connected system. And I've got some things blocking my view here of my own text, sorry. We're using technical tools here for the webcam, or for the webinar that we're unfamiliar with. Sorry about that. All right, so surge travels through the entire system, speed of sound, and if it's unmitigated, that can cause really severe damage. And different designs of different check valves and relief valves have different transient behavior, so it's important to keep that in mind if this transient behavior is causing problems. And it's desirable, of course, to have some tools, AFT impulse, to accurately predict surge levels before you actually go out and test these. We want to give you the tool to know if it will work, obviously. So basics on surge, again, they travel at some wave speed, and there's a simplified equation, the Joukowsky equation, that relates a change in velocity to a change in pressure. So if, for example, you're closing a valve, you're changing that velocity from some steady state velocity to zero. You have some known fluid density and a wave speed, a sonic velocity of information, propagation through a fluid or fluid pipe system. And with that information, you can estimate a change in pressure. It is just an estimation. It's not always conservative. It's easy to misapply. We have a lot of content on that on our website and elsewhere. But For this presentation, we're just going to say to do this properly, you really need to do a full simulation system level with something like the method of characteristics that something like Impulse uses. We're not going to really talk about that more, but the Joukowsky equation provides an easy to understand estimate of surge levels and why this is all important. Again, communication time. These waves take some non-zero time to travel throughout the system. They have to travel to a system boundary and back to the device that caused the wave for there to be any pressure relief. And essentially what that means is that if a valve or any other device for that matter moves faster, so the complete movement, so open to close or close to open, is faster than this communication time, then effectively it's the same as an instantaneous open or close. Relief valves, check valves often react a lot faster than that communication time, so using that Joukowsky approximation as an estimation is pretty reasonable. Again, the method of characteristics, that's a system level kind of tool for simulating this 1D acoustic wave propagation in liquid full piping networks. It's what Impulse uses. It captures the effects of surge and communication time really well. It's industry standard and has been for decades. And again, it's not using this Joukowsky estimation. We're just referring to that as a ballpark figure. So our recommendation always is to simulate things. Don't guess. Don't use the Joukowsky estimation and say you're good. It's not that hard to build a model, so go ahead and simulate it. An example of why this is important. So just quick numbers here. If anyone says, you know, I don't really need to do this, it's probably not that big of a deal. If you had water being pumped and the pump trips, and then some valve closes or opens for that matter against some reverse velocity, this is written for a check valve, but against a velocity of 1 meter per second. So in other words, it's bringing this 1 meter per second flow from 1 down to 0 effectively instantly. And that will generate some surge, travels through the entire system. And maybe somewhere else in the system, hundreds of meters away, there's an expansion loop that has a diameter of 0.5 meter. If you look at the forces on that, we can estimate that, the Joukowsky equation, what the pressure rises. So that is just the fluid density and wave speed multiplied by this change in velocity. And the force would just be estimated again by that pressure delta multiplied by the area of that expansion loop, and you get this pretty huge force, 50,000 pounds force. And this is not just contrived, this is a very realistic number. You can see this type of force in a system from relief valves or check valves operating basically as intended, opening and closing as you might expect. So I'm going to start now just talking basically a summary of the check valve paper. And when I get through this, I'll hand it off to Mark to talk about relief valves. So what is a check valve? It's just really a device to prevent reverse flow. I think we all know what that is. It might be called a one-way valve, non-return valve, any number of things. But the basic idea is that an ideal check valves allows forward flow with no pressure loss and doesn't allow any reverse flow. So simple idea here. And again, a key thing is that it is transient by nature. So an ideal check valve will instantly change position, either from open to closed or closed to open when that pressure differential changes sign. Check valve slam. This is something that we've termed, and other people, term the closure of a check valve rapidly against a non-zero reverse flow. So this is not necessarily referring to the check valve face slamming into the check valve seat. That's also a concern, but this specifically is about the fact that check valves take time to close, and because they realistically take time to close, flow will actually reverse through the check valve before it closes. So an ideal check valve prevents all reverse flow. A realistic check valve does not. You have some reverse flow through the check valve when it closes, and just because of the Joukowsky equation, as we see, the pressure surge there is non-zero. So we're calling that generation of pressure surge check valve slam. There's a couple different kinds of systems you might see, a damped or an undamped system. As I talked about communication time, if there is a check valve that takes longer than the communication time to close, that would be damped. And that essentially means that there's this complex relation between the check valve behavior and the whole system behavior. And to model something like that, you need a relatively complicated model, and certainly a system level simulation. Fortunately, most check valves close faster than that, and we would call that an undamped closure. And essentially what that allows us to do is use the Tchaikovsky kind of approach to approximate the behavior pretty well. If you do have that damped system, you need a more complicated model. So you might need to use something like a physics-based check valve model. AFD Impulse has these, so we have a pretty sophisticated swing check model and translating nozzle plug model. You can put in a lot of terms here for, what are the physical properties of this device, what kind of torque is acting on different angles, things like that. It's a lot of data, and it's even with all of that data, it's still a relatively simplified model compared to the real physics, you might say. So to capture all of the behavior is difficult, but this still has maybe inaccuracies. So just be aware that this isn't a panacea. More boxes to fill in doesn't necessarily mean better. So use that when it makes sense. Most of the investigation on this paper was into this dynamic characteristic model. In Impulse, this is a button in the check valve window that says estimate basically the closure velocity. And the idea here is that you can do dimensional analysis on the check valve problem and relate a number of non-dimensional parameters. And people, kind of titans in early, development of water hammer simulation looked at these things and they said, a lot of these parameters don't really change that much or can be lumped together. And the bottom equation here is essentially what was recommended pretty early on, that you can relate this non-dimensional reverse closure velocity to the type of valve. So is it a swing check? Is it some other kind of check valve, a ball check? And this other term, this d over u naught squared du dt, which is essentially a non-dimensional deceleration. So the idea here is that for a given type of valve, there's some functional relationship called a dynamic characteristic between these non-dimensional reverse velocities and accelerations. So these non-dimensional models can be easier to handle computationally, but they can hide real physical behavior. So you might have two dimensionless characteristics that can vary substantially between two valves of apparently the same type. So two swing check valves may actually behave quite a bit differently. And two valves with maybe identical non-dimensional characteristics will potentially give you dramatically different peak absolute surge pressure. So simply maybe if they're a different size of valve. So we would recommend always using dimensional data. It can be hard to come by in the literature, at least, because people like to make it non-dimensional, since it's maybe more fun, more easily put into simulations, whatever the case may be. But we would say use the real numbers if you can. This is an empirical model, so be aware of and take care of if you're using just a curve. The behavior of a check valve is relatively chaotic. It's a complicated thing that's happening and happening rapidly. And we're trying to summarize all of this behavior with a pretty simple relationship. So you can see here an example on the right of the scatter that you might see for some of these tests. So this is a lab test done decelerating flow through a check valve and measuring the closure velocity that is reached. And you see a lot of points around the graph, and someone just draws a line through it. And sometimes you'll see this data, maybe this exact data that's on the slide right now, republished with just a line. So be careful if that's what you're looking at. There's also a lot of variability maybe within a particular check valve type. So again, this image on the right is for a number of different ring type nozzle valves. And they have obviously pretty dramatically different closure velocities for the same deceleration. This might collapse down closer to a single line if you're using non-dimensional data. But again, this serves to show that different closure velocities will have dramatically different surge. There's no reason not to use this dimensional data. if you can. So this data has been collected since at least 1980. It's not common for manufacturers to do this kind of test, so it's usually done in a specialized flow lab. And the actual test conditions, the dimensional data, things like that can be lost over time through republication. And it's important to know what the actual original test conditions are, especially if it's a non-dimensional valve. There might be a dramatic difference between, you know, what was tested in the lab was a 3-inch valve and you're trying to scale that up to a 20-inch valve. That may be dramatically different. So a big goal of ours with this paper was to go through and categorize a lot of this data. There's a lot of charts in the paper, a lot of data that we crunched, but this is kind of the summary chart saying for different types of valves that we found in the literature, what kind of range can you expect for them on a dimensional kind of dynamic characteristic chart. So you can see here that some types behave maybe a little better than others. Generally, a swing check is better than a ring nozzle type check valve, but there's a lot of overlap here and just a lot of range. So be careful, especially in impulse, if you just say, well, I selected a swing check or I selected split disc. If you can come back later with the actual specification and put that data in, that's always a good idea. And pretty quickly here, I'm going to go through how we calculate deceleration, what that means, and basically how this model is applied. So if the velocity decreases linearly, like the graph on the left here, it's pretty easy to calculate the value for deceleration. You take that over to that chart, deceleration versus closure velocity, and essentially just look up what that closure velocity is. And you could use that with the Tchaikovsky equation to estimate a peak surge level. So it's a pretty simple idea here, but when you apply this to real systems, things get relatively complicated. So this might be something like a velocity profile you would find out of a real system, out of a model, or measured field data, maybe after something like a pump trip. So this velocity over time behavior is clearly not linear, so it's not so clear what to use. And there's just a number of options. I'm going to go through these quickly. Is you could just start at the beginning of the simulation. Maybe that's when the pump trips, but the velocity hasn't really started decreasing. So you could start at the point of first significant reversal. You have to define what significant means and may still not be related actually to the closure of the check valve. You could use an approximated instantaneous acceleration. This is kind of a problem with a discrete numerical simulation like impulse, because you can have noise in the simulation and that could easily throw this value off quite a bit. You could use what you might call the last significant reversal. But there's another item here that kind of glossed over before, is if this is above the fully open velocity U naught. So this U naught here is the velocity required to keep the check valve fully open. So if this was a swing check, any velocity at or above that value would be forcing the check valve face up against, you know, its upper rest. And if velocity is changing above that, nothing's happening with the check valve, so that may not be meaningful to do this. You could use a specified time before reversal. That value should be at least equal to the natural closure time. Again, that's something that I haven't defined until now, and that is essentially what would happen is if you, again, for the swing check valve, just in stagnant flow, open the check valve and let go of it, how long would it take to close? So if you're using a value shorter than that for this specified interval, that's maybe a little suspect. Maybe also you could use the value once the minimum to open velocity is reached. The valve can't close earlier than this, but it also doesn't mean it must be closing just because it reached this velocity. You might have changes in velocity again after this, after it crosses that. So the general kind of conclusion we came to is that you shouldn't use velocities above this U naught. The valve's fully open there and it can't be closing. Instead, you should calculate a deceleration from when the velocity drops below the minimum to fully open line. And if the time to closure above from that point is longer than the natural closure time, a specified interval equal to that natural closure time should be checked. And the keyword here is checked. So basically, if the time between the velocity slowing below the point where the check valve has started closing to the time where it's fully closed is a really long time, well, then it's probably not really closing evenly over that entire period. So you might want to look at a shorter time period right before closure, but not too short, hence this natural closure time. And then, look at both of those and use the conservative value. If the velocity is always below that U-naught, use the last significant reversal. And effectively what all this says is take the most severe deceleration that can be calculated and use that. It's a very empirical model. Play it safe, use what's conservative. So this model in Impulse, it's a pretty simple idea here. Again, we call this estimate from fluid deceleration. You select that and you have a few options. You can select from built-in data that's either non-dimensional or dimensional. And you can also define user-defined dimensional data. I would say these are kind of recommended bottom to top here. If you have user-defined dimensional data, you should use that always. If you can use the dimensional data, you can use that or should use that. If we don't have any dimensional curves that would work for your check valve, but we do have a non-dimensional one that would work, you can use that, but prefer the other options. All right, and as you can see here, there's a deceleration calculation interval. If you want to use that, it's optional. If you choose non-dimensional, you do have to put in this fully open velocity to fully open the valve. All right. This model, despite how empirical it is and how simple it may appear, it actually works quite well. So we do have a case study, a technical paper on our website, an investigation that was done here with Impulse, looking at some check valves, different types of check valves installed in a municipal water system outside of Barcelona. And the field tests here in black were compared with this dynamic characteristic model in Impulse, shown in blue. And they get agreement within plus or minus 15% for the peak surge, which in terms of the type of simulation that we do, we would consider excellent agreement. You can also see in these graphs here the dramatic difference between a swing check valve and a nozzle check. One of these clearly behaves better in the sense of not causing large amounts of surge. The scale here on the two graphs is the same, so you can see a dramatically lower surge with that better check valve design. So speaking of check valve design, just very briefly, there are often trade-offs between steady and dynamic performance, but it's incorrect to say that you have to choose one. Of course, we recognize this is often about capital expense. A valve that behaves well in steady state and has excellent dynamic performance is probably more expensive. And for that reason, maybe you don't always need it. But there are some situations where it's more likely that you're going to need one. So maybe certain types of surge events like pump trips with multiple parallel pumps operating, or pumping against a rising main, or just if it's a critical, sensitive application, you might want to reduce the surge, but you may not need to spend the money on that. However, we would say the second bullet point here, if you are running a check valve in a liquid service and it may slam, you should always check to see that your assumption is okay. Don't just look at it and say, yeah, this is not a critical application, we don't need to do any analysis. You could really get yourself in hot water doing that. All right, and with that, I think I will pass it over to Mark to talk about relief valves.
Sure, yeah. Okay, so this section of the webinar here will be focusing a little bit more on the relief valve paper. So starting from a similar place, what is a relief valve? Put very simply, it's a device that's designed to vent fluid at the kind of recognition of an overpressure or at some kind of high pressure in order to mitigate it. Conventionally, you see that these are used for a lot of slow transient type of behaviors. So that might be like thermal expansion of liquids. That could be, you find them on boilers often, if gas pressure gets too high, fire relief cases. But you also see them for, in liquid systems for if pump discharge is blocked, some things like that. So you end up reaching, deadhead cases. Throughout literature, there's a lot of different kind of types of these, and they all have their different strengths and weaknesses. But in general, they kind of fall down to two different types of devices. One is the reclosing device, which is once you see the overpressure, it cracks, relieves fluid, and then it will reseat, which will allow it to reopen later on. And then non-reclosing, which is your one-use type, so that would be your rupture disc. Once the overpressure is exceeded, you need to replace it or reset the pin or something along those lines. But I think that a really important part of this is that we specify that conventional relief valves are for slow transients. Usually there isn't a lot in literature or out there because relief valve designs aren't specified for mitigating surge. So for faster transients, things that we would see specifically with impulse, usually the kind of rule of thumb, at least from a standards perspective, like API 521, relief valve handbooks, they just say to avoid surge, which is great if you're able to do that. I mean, obviously the best way to mitigate surge is to try and prevent it entirely. But if you're in some kind of situation where surge and relief valve interaction is unavoidable, it can cause a number of different problems. It could blow out a relief valve. It could bypass the relief valve and still damage your system. It could cause the relief valve to chatter or flutter. And also could cause it to open up at the site of the overpressure. And that opening causes a downsurge, which causes more problems. And these interactions can rapidly get out of hand because you have a very large, complicated, complex system. And it really relies a lot on kind of system level interactions with the relief valve. So in reality, it's important to weigh, the severity of what is causing a pressure surge or these anticipated pressure surges in your system. And you need to see and consider how it will react with kind of these sort of unintentional transient devices like relief valves and check valves. Similar to check valves, the way that we recommend to do that is to perform a system level analysis. We recommend running simulations. Obviously, AFT impulse using method of characteristics is one such, simulation for that. But it's very important to, characterize the balance between your system as well as your relief valve itself. So there needs to be some kind of way to talk between them. AFT impulse does have that. And there's a number of different ways to do that, which we go over in the paper. AFT impulse really follows these two kind of mid bullet points here. So modeling a relief valve usually is done with some kind of a loss equation. It could be your loss coefficient, CV, KV, or if you can get performance curves, lift performance curves, or loss coefficient versus relief valve opening characteristics provided by a manufacturer, or if you could attempt to estimate them, usually those are going to be your best bet for using a one-dimensional simulation like AFT impulse. For kind of more intense modeling, you would find it more in higher dimensional software or possibly in vibration analysis. You might be interested in a force balance on the plug itself. And usually you would just try to find some way to tie it between the relief valve opening and the inlet pressure. As long as you could do that, you could still technically use it in a one-dimensional simulation, but a lot of times it's overkill for what we're looking for in a systems analysis. So within impulse, we have a relief valve junction, it's really characterized by these two different tabs here, the valve model and the loss model. Valve model is a little bit of kind of a misnaming. It's really more of a relief model. So it's you tell us how you want it to relieve, and that encompasses internal. So if you want it to be considered a part of the system, if it's exit, if it's venting to system, if it's inline, if the effect is kind of by proxy to the system without requiring a short riser pipe. If you need to define models or opening closing profiles or characteristics, if you would like to use specific a pilot operated profile, things like that. And then also defining your set points, which are, for relief valve engineering, is obviously vital. You need it to open at the right time for whatever overpressure you're attempting to mitigate. And that really just encompasses the relieving tab. You also have the loss model tab, which is where you control all of your valve characteristics. So that would be your closing and opening rates, your CV, your K factor, everything that's going to determine how much pressure loss you're going to get across that. So because these aren't as well studied within the standards, usually it's just kind of advertised that you should go out of your way to avoid them if you can. There's not as much in the way of kind of papers that go into more detail on these types of things. So for our paper that we wrote, it was more we were more interested in determining, well, how do relief valves react to surge and these kind of higher overpressures. And so one of the common cases that you hear with relief valves for an overpressure that it wasn't designed for is a chattering case. So we have a really simple impulse model here where you have a 2,000-foot pipe. You have a supply pressure coming in 100 psi, and you are discharging through an exit valve into atmosphere. And we just have water that's flowing through this. And along this 2,000-foot pipe, we're going to stick a short connector pipe and a relief valve that also vents to atmosphere. And we're going to slam the exit valve in order to generate a surge. The surge will travel back up the pipe, and a relief valve is not designed to handle this surge, right? Because it's designed for other overpressure scenarios. So we've instead sized it for a pump deadhead event. So in the event of like a blocked discharge, and we're going to have it fully open after 1 second with a set pressure that sits right above where our supply pressure is. And when that surge wave comes back, as we can see from this pressure transient graph here, you can see that the surge wave will reach the branch, and the blue line indicates the velocity that is actually flowing through the relief valve. At that time, you can see that it cracks open at about half a second. And that's in response to the pressure rising at the branch, which would be the red line. As the pressure rises up in the branch, eventually it reaches a point to where it is relieving enough fluid and it's able to drop the pressure back down. But as the pressure drops, it falls below the reseat pressure, which causes the relief valve to close, which raises the pressure, which causes it to open, which simulates a chattering effect. So as you can see that the this kind of wave reflection comes back and will end up causing an instability. And you can see beyond about 0.8 seconds, AFT impulse isn't even able to handle it anymore. It gets out of control. So impulse is able to handle these types of chattering events to some extent, but it's more likely to see these, and you need to be aware of them specifically if you're designing for a surge. You might have other surge mitigation devices in your system, but not accounting for a relief valve interaction could cause some kind of effect like this. But as we've said, relief valves are designed for overpressures. Surge is a type of overpressure, so it does beg the question of, well, why do we advocate that they aren't able to handle surge? And so, that was something that we thought would be worth investigating as well. I mean, would it be possible to take a conventional relief valve and try to design for it to crack and mitigate for surge? So we have a very similar system here. We still have the 2,000-foot pipe. All we've done is we've changed the supply pressure upstream to be 300 psi, and we've changed the relief valve. Instead of opening over a second, now it opens in fully 50 milliseconds, which, if any of you are familiar with relief valves, you know that is exceptionally fast, right? But we want to be able to get on top of that surge that comes, flying by. We changed the set pressure and the reseat pressure to be the same, so that once it sees that surge wave coming by, it's able to crack open immediately. And as you can see from, for the case of not having a pressure relief device versus having, this rate limited opening 50 millisecond PRD, you'd see that it's actually able to mitigate surge. So then it begs the question, okay, well, if this is possible in this context, well, then why don't we see this more often? Well, there's a bunch of different reasons. In reality, this is an incredibly simplified system, right? We have one surge event that is causing a transient that passes by your relief valve and cracks it open. The relief valve is designed for that surge event. What happens if you have a network of pipes? What happens if you have equipment on the way there? What happens, if you're trying to get this relief valve to open quickly enough and you can't find one that is able to open fast enough, right? So really what we see here is we see an incredibly idealized case. And if we compare for this exact same situation, but now we're going to open it at 50 milliseconds, 100 milliseconds, and 200 milliseconds, you can see the yellow line on this on the right-hand graph here being the 200 millisecond opening. You can see that now it's unable to shave that peak off like it needs to, and you still have approximately 700 psi of pressure that's that's still affecting the rest of your system before it's able to actually relieve it down to a manageable level, which would be unsatisfactory by surge mitigation standards, right? So it's important to recognize that the faster a relief valve can open, the better it can reduce the peak pressure from a pressure wave. It's what's known as peak shaving. And we see that, as we speed up our relief valve, our conventional relief valve opening, yeah, it's able to mitigate surge, but this is an incredibly idealized situation. So now begs the question of, well, what if you tried to take a relief valve and not take a conventional relief valve? What if you designed one explicitly for surge? And that was why we worked with Jans at Mockfeld, and that was his primary contribution to this, was something that is known as a surge relief valve. So surge relief valves are specifically that are designed for surge relief. They are not designed for other conventional scenarios. Because that is the use case that you're designing for, it is often better understood as a pressure sustaining control valve because you place it at the location of the surge. The idea is the valve itself actuates in order to try and mitigate the surge wave that comes passing by and protect the downstream side of your system to prevent that supply pressure from taking the full brunt of your pressure wave come passing by. So it forces the inlet pressure to whatever your pressure set point is. If it exceeds the set point, then it will attempt to actuate in order to try to drop it back down. And that's what allows surge relief valves. As you can see over here on the right-hand side, you can see there is a pilot-operated surge relief valve here on the side. This is Mockfeld's example that they provided for us. But it allows it to respond to water hammer of different pressure magnitudes and steepness, and to consistently shave off that peak. It's able to act fast enough to adjust its opening with the pressure as the wave passes it, which makes it unique in the sense of it's rate limited. You don't have to be worried about rate limits not being fast enough to mitigate your surge. But this is an incredibly idealized case as well. This is you are designing for surge mitigation, and it becomes a surge mitigation device, like gas accumulators and other types of devices as well. So what we wanted to do is, working with Mockfeld, we wanted to compare these different results of not having surge relief valve versus having surge relief valve, and the 50 millisecond kind of idealized conventional opening case. And as you can see here on the right, the yellow would be your unprotected case. The blue line is the surge relief valve, and the and the red is the 50 millisecond opening. So we have the exact same system that we had before. We have a surge relief valve that's still going to open in 50 milliseconds. We've sized this specifically for surge, and the set pressure is 330 psi. You can see that now our system up in the top right, instead of using a relief valve model, we put a pressure sustaining valve up there to try and control the pressure there. And you can see, based off of this transient pressure graph, it mitigates it quite well, on that upsurge that comes by. However, one of the caveats that usually comes from surge relief valves is that they're designed to handle a single upsurge that comes by, and it takes them a little bit of time for them to be able to reset and reseat. And so what you end up seeing is as the wave, as the downsurge continues up to our supply pressure, up towards that 300 psi, and reflects back, what you see on this the surge relief valve is that the downsurge comes back and it's not able to control that pressure as well as it's coming back. So there are trade-offs with this type of valve, of course, but you can see that it handles the upsurge quite well and it's able to keep it within under your allowable pressures. And yeah, so most of what I just said here, but surge relief valves are sized specifically for peak shaving of surge. You can see that it didn't handle the downsurge as well. A 2-second closing was a little bit too slow in order to kind of keep that pressure level where we really want it to be in a surge mitigation situation. So in order to conclude these, so kind of going back to what Scott had said, we're interested in simulating check valve slam with regards to a systems level design, check valves closing rapidly against a non-zero flow, and we're also interested from the relief valve side of relief valve activations that cause potentially dangerous pressure surges or exacerbate effects that we would see. A lot of times these are overlooked because they're not primary events. Usually they are passive devices or passive transient devices that aren't accounted for. But you always need to consider them whenever analyzing your system for, for the possibility of surge getting out of hand. For all but the simplest cases, you would want to use a system level analysis like a simulation software. Impulse is one that provides such as that, and your rule of thumb approaches aren't going to be sufficient. Using the Joukowsky equation is a good estimate, but oftentimes it can still provide you with misleading results. So we still advocate that you would want to simulate your system to the best of your ability and use as accurate information to represent your system. And then check valves and conventional relief valves are not surge mitigation tools. They should not be used for primary surge mitigation. You need specialized surge relief valves like the surge anticipator valve, or possibly which is an option in Impulse, or the surge relief valve, such as the one that Mockfeld had presented. It's still very, very important to consider these types of things in your surge analysis whenever you are looking at your systems. And I believe that that's the end of this. And I think at this point we can open the floor for questions.
Yeah. Yep. Yeah. If there's any questions, we'd be happy to address those.
How clean does the surface have to be to use this type of relief? Clean in.
I assume you mean by clean service like that it's not a slurry or something similar.
Yeah. It kind of depends. Our understanding is that usually it's dependent on a system by system basis. For Mockfeld, I know that they explicitly designed their systems, they explicitly designed their surge relief valves for specific systems. So they would actually analyze it and be able to tell you, oh, maybe this is too corrosive, or maybe you would have chemical reactions in this or something like that. Usually you would rely on the relief valve kind of designer expert in order to decide those. I'm not as familiar with it. I would assume that they can be used, but it's a case-by-case basis. So. Sorry, give us some time here. We're reading through these questions. Oh, surge relief valves only mitigates upsurge and not downsurge. Usually that requires a better sizing. So for the simulation case that we had run, we knew after working with Mockfeld that it was designed to respond very quickly to the upsurge. The downsurge, it takes a little bit of time. So it depends on the communication time specifically. It can mitigate downsurge, but usually the surge relief valve needs a little bit of time in order to kind of reset itself to be able to mitigate both. So it's not a perfect model of it, which is why we had to use the control valve for that case, but they are supposed to be able to handle downsurge as well. But we had, as I said, some slower closing rates than
normally you'd probably see with those types of valves.
All right, and I see a couple of questions from earlier on. One is just, why are we trying to avoid surge a little bit? What is the detrimental effect this pressure has on the system? Maybe from closing a valve like a check valve too quickly. And the simple answer is, if the pressure is high enough, it can burst pipes, it can damage equipment, it can knock pipes off of supports, things like that. And obviously related to pressure is force. So, you can have this radial force that might serve to burst a pipe or damage equipment from the inside. But you can also have what I would call it a transient longitudinal force on something like a expansion loop. So obviously a very common configuration in the system, and the types of events that we're talking about in this presentation, in these papers, you can easily see that force exceed 50,000 pounds or something higher than that. It's not outside the realm of possibility. So that's the reason, is to protect the system. A second question here I see is about the check valve values. And we'll read this a little bit because it's a great question. Is due to the lack of manufacturer's data, we only use basically estimated data from a table. So for example, a swing check valve might say the reverse closure value is -2 feet per second. A silent check valve is -0.3 feet per second. And the question that I see here, a really key one, is how far is the use of these values from the possible reality of check valve maybe behavior? And that's a great question, and I would say that is why we wrote the check valve paper, as we talk about that variability and what you should do. The key thing here is to recognize that it's all very empirical and to use a conservative value, and also recognize that the -2 feet per second may be the value for a particular swing check valve, but different swing check valves may have a pretty wide variation in that. One might be -1 foot per second, one might be -4 feet per second. So just be very aware of that those are not kind of standard values. They are very much ballpark estimates. And if you can get better data, or at least check different sources, do that. And the source that I would point you to get more data is our paper. Actually, we make a lot of references to studies that were done in labs in the literature. So, all right. So we don't see any other questions. Certainly, if you have any about this, send those our way. Send them to support at AFT. They'll make it to us, and we can get back to you. But not seeing any other questions. It's been great having you all here. Thanks for joining us, and we all hope that you learned something.
Have a good rest of your day.